Please briefly summarize your industry education and professional background.
So I've got a kind of mixed industry academic background. I worked for Esri as an industry manager of AEC, or Architecture, Engineering, Construction. Worked at MIT as a planning professor teaching GIS, and I'm now back working for a startup. So a little bit of everything. Geospatial generalist, I guess, is how I'd characterize my background. Go back far enough, I have a background in biology. So my PhD is in fire ecology, actually.
How does HEAVY.AI fit into the infrastructure industry?
So we enable very large data set analysis, and we do it in a kind of interesting combination of ways. So part of us is very old fashioned. So we are a SQL database, and we work like every SQL database you've ever seen. But we work on GPU. And so we run 100 times faster in many use cases than what you're used to. And so how you use that speed depends on you. You can use it for simulation, but a lot of folks use it for interactivity. And so in particular, what I'm seeing is a lot of engineers taking information that used to be collected in an aggregate fashion or aggregated immediately, and using the disaggregate form of that information. So if you want to talk about asset networks, think about every piece of conduit on every line span of every utility, in the country, and every piece of equipment. That stuff adds up quickly, and as soon as it gets placed in the environment, as all the civil engineers here know, it ages, and the stresses on it are environmentally related. So if the thing is baking in the Arizona desert, it has different behavior than if it's freezing up in Anchorage. So I think of those as kind of, like the assets released into the environment, and then they each start, and they might start identical clones, but they each become very grizzled characters over time. And so the general thing I see happening that this GPU acceleration enables is that a lot of this infrastructure was put out there years, decades back, hasn't been fully monitored. Sometimes you can't know even what the age or the part number is. But increasingly, we've got all of these new remote sensing technologies that are then giving us a live picture of at least indicators of the quality and performance of those things in the wild.
Can you explain a little bit more what the aggregate versus disaggregate means?
Imagine you run a utility like PG&E and you have 100,000 miles of power line. That's a lot of power poles. And there are 120 million trees in the immediate proximity of that equipment. So if you want to know, is your equipment in good shape? Are you at risk of a strike tree incident where a tree falls onto a line? You've got a lot of stuff to keep track of. And the traditional way of dealing with data at that scale is you would aggregate up and say, with remote sensing, well, what have I got within a 30-meter pixel or a 1-kilometer pixel? What's the risk level? But the problem with that is that it hides a lot of risk, right? Because it's not the average conditions in a 30-meter pixel that determine whether a tree will fall. Trees are individuals, and they live or die individually. And in particular, the ones on the edge of the forest are actually more vulnerable to different conditions. So the difference is really the ability to keep granular data on tap always. Doesn't mean that aggregates aren't still useful. They are, just that they need to be carefully drawn. So the ability to find essentially one tree out of 1,000 that's going to hit your power line, that's really important, increasingly important, that you're looking for the anomaly, not just the average.
How would you describe accelerated geospatial analytics, and how can they help in infrastructure applications? Can you cite some specific examples?
A couple that I like in the infrastructure domain are a group of University of Michigan folks mostly that applied us to the Flint water crisis. And so they had very partial information on which pipes feeding which houses had lead in their water supply. They built a machine learning model to predict that better, and made that into a public information site that anyone can go to, any member of the community, and get an estimation of what's the best available information as to the likelihood that there's an issue at any individual address. So it's a very traditional risk analysis, but then with this public face to it, right, that you can get directly down to the consumer. And I guess I would say, like, as framing for that, I think we have a really historically high level of distrust of both government and expertise. And to me, we can bemoan that, but one solution to it is provide people direct access to individually specific data. So if I'm a homeowner and you tell me the average lead in the water supply is, some number over my city, that's a lot less compelling than telling me that, there's a 75% chance that I've got lead in my water supply, right? So to try and to use this technology to make messaging direct to the consumer will help us a lot, because I think people tend to trust or at least and act on specific information more than they do general information.
How has technology changed the infrastructure industry in the past, and how do you see it affecting the industry's future?
The big trend I see is ubiquitous sensing, and I'm not the first one to mention this. It goes by many names, but I guess I would say I've in my career seen infrastructure management going from kind of a database that was non-spatial to one that was fully spatial, to one that's now spatial and temporal, to one that's spatial and temporal and includes the adjacent environment conditions. And each one of those kind of increases in scope, has been technology enabled, but each one gives you a much, an increasingly better idea of what you really need to know about an asset in its installed location.
So what advice or tips could you give our engineering audience that they may not already be doing in terms of using analytics or other related technologies? How can they learn more about them and start to use them?
Depends where you're coming from, of course, but I guess I would say, even as somebody that's been dealing with remote sensing data for 20 years, I'm continuously surprised at new stuff coming from that field. So if you're not familiar with remote sensing and what's currently capable, don't let your opinion from 3 years ago influence you, because probably the answer is different today. It's really fast moving. So I would definitely encourage people that haven't used or looked at remote sensing data in a while to take a look at what's now available. And I would say the same about LiDAR. So if you haven't used LiDAR, my initial experience with it was almost a panic mode. I was doing a project for the state of Florida where we had scoped everything for 30-meter pixel data. And along comes 7 years into the project, or 5 years into a 7-year project, along comes 4-centimeter LiDAR. And my reaction, of course, was panic, and then running around trying to find a tool, because of course my budget didn't go up by 10,000%. So I was being asked to do more, more with the same budget. But it's really interesting and relevant data for a huge class of engineering problems. It's not perfect data. It's got its own idiosyncrasies, I guess. But if you haven't used it, I would urge people to get familiar with that, see what it can and cannot do. And it will change your attitudes towards tooling. Did mine. So that's actually how I ended up in my current job. I was a consultant running a small consulting practice, and I reached for traditional tools for dealing with that LiDAR. Quickly realized I was drowning in the data, that I wasn't getting anywhere. And so that led me to look at GPU analytics myself to solve that problem. So I think definitely take a look at where the remote sensing data is going, and where passive remote sensing like optical, and also where LiDAR stuff is going.
Okay, so let's say that they're not sure how to do that. Is there ways that they can try and find out more information on their own? Should they look to consultants, or would just be some tips there?
Sure, depends a lot on how much you want to DIY, but if you want to get your hands dirty with it, you can actually download our software for free and see what we can do with that data set. You can also use a number of, I'd say, Kaggle is an interesting website. So there are Kaggle competitions out there that you can take a look at, which are, kind of, they're competitions, but then there's an analytic workflow underneath. So you can see, all right, what's the best practice for example, using machine learning on LiDAR data? Pretty complicated topic. I don't advise you to do that yourself for the first time by hand, but go look at what other people have done and are able to accomplish. And if that's interesting, relevant then to your business context, you actually have the code in front of you and you can dig in deeper. But you can take a look at the results, for instance, of these Kaggle competitions and get a good sense of what's currently possible.
So if they're concerned about all this data that they're dealing with, Might they be using cloud computing to take some of this off their hands so they don't have to worry about the computing sources on their own end?
It's not necessarily true that cloud computing scales linearly, right? And so we all wish it did, but it doesn't. And where it doesn't is when you get into big data issues. And the main issue with big data is it's got a level of gravity to it. So if you have, I don't know, 100 megs of data and it's in Frankfurt, Germany, fine. You can bring it to your local machine in a few seconds and download it and deal with it. But if it's, 2 orders or 3 orders of magnitude more data, like the European Space Agency's Sentinel-2 program, what you want to do is you want to figure out how to move your compute to the data. So for example, 2/3 of the world is cloudy on a given day. So 2/3 of that imagery sitting on that, on that website, you probably don't want to download. But you can basically, that's the beauty of modern cloud compute. You can choose where you do some of this compute. You can do it close to the source data if it's really big, and then filter out, for instance, cloud-free images and only process those. But you will at some point get to data volumes that are really large data volume. And that's, of course, where GPU analytics comes in. So just as a kind of starting comparison, your typical good desktop machine might have 16 or 24 cores of CPU. A typical graphics card has 20 to 40,000 cores. And so for geospatial data in particular, it's quite easy to make parallel or to analyze in parallel. And so that's where GPU analytics comes in, that you have a lot more ability to parallel process natively. And the other thing people don't realize is the bandwidth on these GPUs, their ability to move data around. Particular system we're dealing with now, NVIDIA's kind of new A100s, or last generation, not the new ones they just announced. That's on the order of a terabyte a second of data movement. And the fastest disk that I know, which is really expensive, fast disk technology or solid state disk technology, is 300 megs per second, 300 gigs per second, sorry. So anyway, in between the fastest disk money can buy and a normal GPU, there's still, at least an order of magnitude of difference in speed. So ultimately, when the data gets big enough, you do need to figure out how you're going to parallel process on it. And cloud doesn't solve that for you. That's basically where you have to start to reach to GPU, because you will have to pay attention eventually to the fact of where the data is, or at least where it starts. And then you can be clever and run, hopefully your software on the cloud, including our software, where close to the data. But when the data gets big enough, you do not want to be spending your days like moving it around, particularly moving all of it around. You want to try and get your queries, get your filtering close to the original source, and your life will get a lot better.
Okay, great. So you talked a little bit about the electric utilities. Are there some other industries that are using this kind of technology? You can cite some specific examples.
Yeah, another favorite project in the utility space is the city of Virginia Beach, and some work that was done there, again, with kind of academic USGS local partnership. But they took the national weather model, which I believe is on the order of 10 or more terabytes of data. And they cut out just the parts they need for Virginia Beach to figure out hurricane-based flooding. And so they took this massive government model that is, it's kind of widely available, but again, it's big data. So do you want 11 terabytes of data on your laptop? Probably not. But they were able to use then our software to cut that down to size, pull out just the Virginia Beach part of it, which I believe was 25 years of historic data, and then a water model they ran at 5-meter resolution, and they could predict, built a model basically to predict local flooding based on this national weather model data. And I'd like to see more communities do that, right? But they're lucky they had a USGS guy that was working local government. Often it takes somebody like that to know, hey, there's this massive resource out there available from USGS. We could actually use it to solve our local problem. But I think that that particular group is a really good example of using the power of really big geodata and modeling projects, but then applying them in a local use context to figure out, which local streets are subject to flooding and what to do about it. One topic we didn't get to, and I'm increasingly fascinated by, is we have a lot of nearly real-time data now about where people are, and that has a creepy aspect to it that gets a lot of press, but it also has a really good public policy use, which is we know which infrastructure people are using. And so I think that capability of understanding the human part of the equation of who is using what infrastructure is really important. And that gives us an ability to do a better job kind of at traditional infrastructure planning, but also a number of the emerging issues like environmental justice or infrastructure justice can really be well addressed by taking a look at who has access to what infrastructure, who doesn't have access to infrastructure. And that is something that I think most engineers have the technical capability to do. I'm not sure if they realize they have the data available to them, but that's one of the use cases the telcos, for instance, are using us for, is they're planning where they put their assets based on where people are day and night, right? Where they would live, work, and play. And we have that data widely available. It's commercially available data. It goes well beyond census because it's got that temporal dimension of when people use an asset, and of course, when there's surge demand on that asset. So I'd like to see more of that used in general in engineering and certainly in civil engineering. So the other aspect where I think we can make really good progress is that we now finally have very good spatial predictive models of climate change, including granular aspects like flooding or drought, and attribution of changes from historic patterns. And so that can be used in a number of engineering applications. But I'd love to see more engineers bringing that to their clients in a conversation about how we can design better infrastructure. It's not always in the RFPs. It's not always in the responsive setup, but there are huge opportunities to build things better given this information, given our knowledge of how the climate has changed, how it will change. And I think the passage of the recent infrastructure bill is a kind of generational opportunity here. So I'd love to see those two themes combined. And I think there's a great opportunity there.